welcome to the lectures on Engineering Mathematics 1, and today we will be talking about the differentiability of two variables, functions of two variables, and this is lecture number 12. So, we will introduce first the differentiability concept for the functions of two variables, and then we will derive necessary conditions for differentiability and also sufficient conditions for differentiability. So, just to recall the differentiability of single variable which we have learned in the previous lecture. So, there were three concepts we have used to define the differentiability of a functions of single variable. So, one was the existence of the derivative. So, if this limit f x plus delta x minus f x over delta x exists, which we call derivative of the function f at x, and it was denoted by f prime x. So, if this derivative exists, we call the function as differentiable. The second concept, which is more general, and we will indeed now use this to derive differentiability of functions of more than one variable. And in this case, we have seen that if we can express this delta y, which is the change in delta y when we make a change of delta x in x, and if we can express this change in terms of this dy plus epsilon delta x, the dy which we call differential was a linear term in delta x, and this was a times delta x. Here the a was independent of delta x, and this epsilon term must go to 0 as delta x goes to 0. So, the third one was useful for testing the differentiability, and what we have seen that if this quotient here delta y minus dy over delta x, and when we take this limit delta x goes to 0 is 0, then we call the function differentiable. So, this was just a consequence of this relation when we have taken this dy to the left side and divided by delta x, taking this limit since epsilon goes to 0. So, we get this relation out of this relation, but this was useful for testing the differentiability in many cases. But what was the point here, that all these three definitions are equivalent for differentiability. So, the existence of the derivative we have seen that implies the differentiability of a function of single variable. But today what we will observe that the existence of derivatives, which we call the partial derivatives with respect to x or y, that is not sufficient for the differentiability of the functions of two variables, for example. So, here just to define the differentiability of functions of two variables, we take this function z is equal to f x y, and this is said to be differentiable at the point x y, a general point x y, if at this point we can express this change in z. So, now we have this z as independent variable on x and y. So, x y here are independent variables. So, if this change in delta y is equal to a times delta x plus b times delta y plus epsilon 1 times delta x and epsilon 2 times delta y. So, this is just the extension of the definition which we have used for functions of one variable. And now, in this case again this a and b, they are independent of delta x and delta y, and this epsilon 1 and epsilon 2 they must go to 0 as delta x delta y goes to 0. So, again we have this linear term and then this quadratic or the nonlinear, rather nonlinear term, because we do not know the what is the dependency of delta x on epsilon 1 and epsilon 2. So, we have the linear term here and plus this rest. So, again here the a and b are independent of delta x and delta y, and epsilon 2 are functions of delta x and delta y, such that this epsilon 1 is equal to 0 when we take this limit delta x goes to 0 and delta y goes to 0. Also, this epsilon 2 when we take this limit as delta x and delta y both go to 0, epsilon 2 must be 0. So, this linear function again, which is a delta x plus b delta y, is called the total differential. We have also introduced in case of functions of single variables. So, here this is called total differentiable of z at this point, general point x y, and this is denoted by delta z. So, now we will denote this by dz, which is the linear part of this expression, and delta z, that is the change in z when we make change in x and y by delta x and delta y. So, this dz, which we call the differential term or the total differential, this is equal to a delta x and b delta y, that is the linear part of this change in z, which we can also denote, because we have observed yesterday that delta x or dx, they are the same because they measure the change in x, and in this case because we have two variables. So, the delta x and delta y or dx or dy, they measure the change along the x and the y axis, while this delta z is the change in the function value, whereas this dz is different, which is the change in the along the tangent plane. In this case, in case of one variable, it was along the tangent line. So, if this delta x and delta y are small enough, then this dz, which is the differential of z at this point, will be a close approximation or will be a good approximation of the change in delta change in z, that is delta z, because this nonlinear term here for small values of delta x and delta y, that will go to 0, and we will have a very good approximation by this linear term, or at least in the neighborhood of the point x y. So, the geometrical interpretation of the differentiability. So, what we have seen in case of function of single variable, that at this point x 0, the value of the function is f x 0. So, this is the tangent line. That means, if the function is differentiable, we have observed that we can draw a tangent line, or in other words, we can approximate this function in the neighborhood of this x 0 point by this tangent line. So, as we see here in the graph as well, in the close neighborhood of this point x 0, we can have a very good approximation by this tangent line, at least in the close neighborhood of this point x 0. In case of the functions of two variables, so we have a similar argument or the extension of this concept. So, if suppose there is a point here x 0 y 0, and then in this case, if the function is differentiable, then we can approximate in the close vicinity of this point by the tangent plane. In case of single variable, this was tangent line, and now we have the function of two variables in this picture, and then we can approximate by this tangent plane, which is actually the linear part, which we have seen in the definition there. So, what are the necessary conditions for differentiability? We will derive now. So, if this z is equal to f x y, this function is differentiable, that means we can express this delta z is equal to a delta x plus b delta y plus epsilon delta x plus epsilon delta y. Then we will show that the function is continuous and has partial derivatives with respect to x and y at that point where we are talking about the differentiability. That means, here that this continuity and the partial derivatives, the existence of the partial derivatives at x y point with respect to x and y, these two are the necessary conditions for the differentiability, because we will show that the differentiability implies that f is continuous and the partial derivatives exist at the point x y. Moreover, we will also see that this a here, which is the constant free from delta x and delta y, this is nothing but the partial derivative of f with respect to x at that point, and this b here is nothing but the partial derivative of f with respect to y at that point. So, let us prove this. So, if we assume that this f is differentiable, that means we can write down this delta z here, which is we have made an increment here delta x and delta y in x and y, and this difference is nothing but the delta z. So, delta z we can express as a delta x plus b delta y plus epsilon delta x plus epsilon delta y, the definition of the differentiability. So, having this, now if we take the limit here as delta x goes to 0 and delta y goes to 0, what will happen? Since delta x goes to 0 and a is a finite number, so this will disappear. So, and again this will go to 0. Here also, since epsilon goes to 0 and also delta x goes to 0, so this term will go to 0 and also this term will go to 0. So, we will have simply, when we take the limit delta x goes to 0 and delta y goes to 0, we will have that the limit of this f x plus delta x, y plus delta y, as delta x goes to 0, delta y goes to 0 is equal to f x y, and this is nothing but the continuity of f. So, to show the continuity, we take a point in the neighborhood and then we take the limit, and this should approach to the function value x and y independent of this how we approach to this x y point by taking this delta x to 0, delta y to 0 along any path. So, that was the continuity here of f, which we have proved. So, what we have assumed that if f is differentiable, then we can express it in this form, and simply by taking this limit we have seen that the function must be continuous if the function is differentiable. So, next we will continue the necessary condition, the second one. So, we again assume that f is differentiable, then we can express this delta f or delta z in terms of a delta x, b delta y, and this epsilon and epsilon 2. And now, since delta x and delta y are arbitrary, we can choose in the neighborhood anything here. So, what we have set, if we set delta y equal to 0 and then divide by delta x, then what we will get? So, we will get this here x plus delta x and then delta y is 0 minus this f x y and divided by delta x. So, that will be equal to, so here a will remain and then here delta y is set to 0. So, this term is 0 and then epsilon 1 because we are dividing with delta x, and this term will go to 0 because we have set delta y to 0. Because this is again we are in the neighborhood of this point x y. So, if we are talking about a point here x y, so we have set just delta y to 0. So, again we are in the neighborhood along this x axis by having this delta x not equal to 0 at this moment here. And so, we can do that, we can take any delta x and any delta y, and this relation must hold. So, what we have done, we have taken delta y to 0 and then divided by delta x, and now we can take the limit of this delta x as it goes to 0, and what we will get, this is the partial derivative, the definition of the partial derivative of f with respect to x, and this will be equal to. So, we have taken the limit here both the sides. So, the limit delta x goes to 0 and here also then in this case the limit delta x goes to 0. So, a is independent of delta x delta y. So, this will remain as a, and this epsilon term will go to 0 as delta x goes to 0. So, we will get this relation that f x is equal to at x y is equal to a. And now, similarly what we can do, we can set delta x to 0 now, and then we can divide by delta y, and again by taking the limit as delta y goes to 0. So, we will get that f x y f y x y is equal to b. So, here if we take this limit now delta y goes to 0. So, the right hand side will be just b because epsilon 2 will go to 0 as delta y goes to 0. So, in this case we will get that the partial derivative of y at x y is equal to b. So, what we have observed now, that if a function is differentiable, in that case the partial derivative of x at this point x y will exist, and that will be nothing but this number a here, which is appearing in the definition of this differentiability, and also the partial derivative with respect to y at that point will exist, and the value will be b, which is appearing here in the definition of the differentiability. So, what we have seen now, that if a function is differentiable, then it must be continuous, and not only continuous, but the partial derivatives must exist at that point where the function is differentiable. So, these are the necessary conditions for differentiability. If one of the conditions, like the function is not continuous, or one of these two partial derivatives does not exist, in that case we can immediately claim that the function is not differentiable, because these two are the necessary conditions, the continuity of the function and the existence of partial derivatives. So, if one of these conditions is violated, then we can immediately conclude that the function is not differentiable. But if the function is continuous and also the partial derivatives exist at the point x y where we are talking about the differentiability, in that case we have to go for the further test, because these are the necessary conditions. Based on these two conditions, we cannot say that the function is differentiable or it is not differentiable, because these are the necessary conditions for differentiability. So, now we will move to the sufficient conditions for differentiability, and in this case, if one of the partial derivatives of z exist and the other is continuous at a point x y, then the function is differentiable at x y. So, what we have now for the sufficient conditions, that if one partial derivative exists, and that is anyway necessary condition for the differentiability. So, we must have the existence of both the partial derivatives for discussing the differentiability. So, this is natural now, because this is a necessary condition that both the partial derivatives exist. So, basically for the sufficient condition, we have to check that if one of the partial derivative is continuous, then the function is differentiable at x y. So, we need continuity of one partial derivatives and the existence of both, because the existence is necessary condition for the differentiability. So, we suppose here that f y exists and f x is continuous. So, in this case we will now observe what is this delta z, the variation in this z when we vary x by delta x and y by delta y. So, we will consider this difference now, and we will see whether we can express this difference in terms of that linear function plus this epsilon delta x plus epsilon to delta y. So, here now moving further, we have f x plus this term, and then we have subtracted this f x y plus delta y, and we have added the same here f x y plus delta y minus f x y, which was already there in the difference. And then since we have taken here the existence of f y and continuity of f x, so we will use these two conditions to prove that the function is differentiable. So, the existence of f y implies that this limit here f x y plus, so here this is the partial derivative with respect to y. So, that means f x y plus delta y, we will make an increment in y, and minus the function value at that point divided by this increment delta y, and taking this limit delta y, that this exists. That is the meaning of the existence of f y, that this partial derivative exists. So, this is equal to f y. And now we can use that idea which we have used in the previous lecture, that once the limit is given, we can define or we can introduce some epsilon, that means that f this x and y plus this delta y and minus this f x y over this delta y is equal to or with minus sign here. So, minus this f x y we can set as epsilon. In this case we will take this epsilon 2 and then later on we will introduce epsilon 1 as well. So, if we set this difference to epsilon 2, then we know that when we take the limit as delta x, or in this case only this delta y goes to 0, then this epsilon 2 must go to 0, because when delta y goes to 0, this is nothing but exactly the f y at x y. So, this we will introduce now, and then we will multiply this whole expression by delta y, and we will get that this difference is equal to f y delta y plus epsilon 2 delta y. So, having this, we will get this f x y plus delta y minus this f x y is equal to this delta y will be multiplied to the right side. So, we will have f y x y and plus this epsilon 2 which we have introduced here, and this delta y. And note that this epsilon 2 which appeared here now must go to 0 as delta y goes to 0. This is the condition because of this limit we have observed. Next, now we will use the Lagrange mean value theorem. So, just to recall what was the Lagrange mean value theorem, we have function which is continuous and differentiable in the open interval a b. So, here f b minus f a over b minus a is equal to this quotient will be equal to the derivative at some point in the interval a b. Yeah, that was the Lagrange mean value theorem we have studied before. And now, so using this Lagrange mean value theorem to this difference here. So, notice that here f x plus delta x and f x. So, y is unchanged. So, y we are not changing, y plus delta y, here also y plus delta y. So, this is with respect to x only, the change is in x, and if we divide. So, this is like f b minus this f a, here a is x and this b is x plus delta x, and divided by the difference which is b minus a. So, in this case this will be delta x, but we will multiply to the right side will be delta x, and the derivative naturally with respect to x, because we are talking about with respect to x, the y is unchanged. So, f x the partial derivative, and at which point here the xi was between b and a. So, here also this argument will vary between this x and x plus delta x. So, we have introduced this theta 1. So, that this will be precisely between x and x plus delta x when theta runs between 0 and 1. So, this theta 1 here is between 0 and 1. When this is close to 0, this argument is close to x, and when this is close to 1, this will go to x plus delta x. So, exactly which xi was doing here in the open interval a b, we have this argument x plus theta 1 delta x for this theta 1 0 and 1. So, we have this the Lagrange mean value theorem now. And now, the continuity of f x, because we have assumed the continuity of f x and the existence of f y. So, this continuity of the partial derivative f x we will apply here. So, if f x is continuous and we take the limit delta x goes to 0 and this delta y goes to 0, then this f x x plus theta 1 delta x y plus delta y will simply go to f x at the point x y. This is what we have used now. So, the continuity of f x will give us that this derivative with respect to x will be f x at x y point. And then again we will introduce another epsilon as we have done before. So, that is f x and this x plus theta 1 delta x y plus delta y is equal to f x at x y plus this epsilon, and this epsilon will have property that this will go to 0 as delta x and delta y goes to 0.